We're now going to see some cases in which limits fail to exist. The intuitive idea of a limit is that as x approaches a, f of x approaches L. We've noted that the behavior of f at a is irrelevant in this context. Remember that this is the formal definition of a limit. Saying that a function f of x has a limit L as x approaches a means that for every epsilon greater than 0, there's a delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is strictly between 0 and delta. We saw what this means graphically using this picture. We changed this function a great deal without changing the limit, because we didn't change the graph inside this rectangle. Well, it's not entirely true. We did, but we could draw a smaller rectangle in which we didn't change the function. But what if we keep changing the function at values of x ever closer to a? Let's suppose that L is 3, and let's just keep changing the value of f at these x values to 4. We keep zooming in and keep changing f ever closer to a. It's worth noting that this function looks more and more like a straight line as we zoom in. If we keep doing this arbitrarily close to a, then we get something that no longer satisfies the definition of a limit, because no matter how small an interval we choose around a, f will always take on values near 3 as well as the value 4, and 4 isn't near 3. What we mean by the word near in this case is really just that 3 and 4 aren't the same number. From this example, you can imagine that a function without a limit at some point is very bizarre. But there are two special ways that limits can fail to exist that are worth discussing individually. In the first case, the function behaves well on each side of a point. In this case, that's x equals 5. But the two pieces of the function on either side of that point don't meet. In this example, the image under f of any interval around x equals 5 will include both 2 and 4, so the limit can't exist. The function's not approaching a single value. But this nice behavior on either side of 5 motivates the idea of a one-sided limit, which is a limit that exists when approaching an x value from one side only. We denote an approach from the left of a with a negative sign as a superscript when we write the limit. This is called the left-handed limit. Similarly, we denote an approach from the right of a with a positive sign and call it the right-handed limit. Note that a function could have one of these limits without the other. A function could behave nicely on one side of a and poorly on the other. Another special case of a limit failing to exist is when the function approaches positive or negative infinity at a particular point, which is another way of talking about vertical asymptotic behavior. Let's look at how the function 1 over x squared behaves as x approaches 0. This is a case where the point in question isn't in the domain of f, but remember that that has no effect on our ability to talk about the limit at that point. No matter how narrow an interval around 0 we choose, the image of that interval under f is going to be everything on the y-axis above a certain point. So 1 over x squared is definitely not approaching a particular value as x approaches 0. It is, however, in some sense approaching infinity, and in these cases we say that the limit equals infinity. This is really just shorthand for this particular type of limit non-existence, even though we use the phrase the limit equals infinity. There are some contexts in which we want to group limits equal to infinity with limits that actually exist, and others in which we want to be precise and say that they don't. We should always default to this one, saying explicitly when we want to consider them as existing. Formally, saying that the limit is infinity means that for any m greater than 0, no matter how large, there's a delta greater than 0 such that f of x is greater than m whenever the absolute value of x minus a is strictly between 0 and delta. We can also define what it means for a limit to equal negative infinity. The only difference is that we now have f of x less than minus m. Be careful though, because the sign matters here in a way that it didn't before. The expressions f of x greater than m and f of x less than negative m don't involve absolute values, so with a function such as 1 over x, we don't have a limit of plus or minus infinity. But we can use the idea of one-sided limits that we just discussed to say that the limit of f as x approaches 0 from above is positive infinity, and the limit as x approaches 0 from below is negative infinity.